So let's look at operations on matrices. And basically, operation research did a video on most of it, like all the operations pretty much. So let's just go a quick rundown of a few things that weren't fully covered, maybe, like mostly like the different properties of matrices and rules of operation. But first, real quick, just to make a mention, the zero matrix has all entries equals 0, just in case it wasn't obvious. So 0, 2 by 3 would be 2 rows, 3 columns of all zeros. Otherwise, there's nothing crazy here. Properties like let A, B, and C be matrices, and let A and B be scalars. Property 1, we have like so many letters that we almost run out of the alphabet, it seems. But no. Like if you add matrices, you can do them in any order. It's basically a lot of it, and A plus 0 would be equal to 0. The negative of a matrix A plus A, matrix A will basically be 0. It's a lot of obvious stuff from normal algebra, a lot of it applies, like A times identity equals A, and I times B equals B. Identity is I, because I is the identity matrix and such. There's a lot of properties here that aren't really too important. Just mostly intuitive, a lot of it. And here's another thing where you multiply. Oh, this is an interesting one though. The matrix A times the sum of B plus C matrices is AB plus AC, but the B plus C, it's showing that you have to keep that order in mind though, definitely. Here's one with scalars, and then a lot of these are pretty intuitive and simple to think of. We have 1 times A equals 1, 0 times A times 0 equals 0. Some basic ideas here. Yeah, that's why normally you wouldn't have all these written out, but it's nice to look at briefly at least this thing. The most interesting one being the last two, A plus B transpose of the sum is equal to A transpose plus B transpose, and AB transpose is equal to B transpose times A transpose. I think those are more interesting and can be useful, but you're not going to really need to worry too much, I don't think. These properties just come up, but that's why they're in a light green, because they're not the most important thing ever. Still good to notice. So in these first several examples, we let A equals this matrix and B equals this matrix. And let I be the identity matrix of order 3. Find each as indicator. So it's a 3 by 3 identity matrix. Is what order means. Order 3, identity means just 3 rows and 3 columns. An identity matrix has a diagonal of 1s and everything else be 0s. So as you recall from operations research video, if you watched that one. So A plus B equals, so the sum of these two matrices, you just add the individual components from each entry. You add entry from A and entry from B in the same position. 2 times A minus 3 times B, well, you multiply a scalar into each of them, and then you add the two matrices, and it's the same process. It just becomes, yeah. I mean, there's not a lot to talk about, especially with these operation ones. Like those first two are very basic ideas. Like it's basically algebra, but in a slightly different sense. Like you're worried about matrices, you have the rows and columns to keep them in mind. So A minus lambda times I, lambda is a scalar. So this one's a little bit more interesting. I just do negative lambda times and just add them. You could just do lambda times it and then you just do minus it, but it's the same thing. And all you do is get, the diagonal really changed from, it's just subtracting lambda really. The reason this comes up is because this is actually used later on in the course. Like you'll see this at times, the scalar lambda used. like later in the course when you get into eigenvalues and such. It becomes useful again, this matrix type. A minus lambda times I is format is used, but that's not important right now. And A transpose, again, so from operators, so transpose is just you flip the rows and columns. You make the rows columns and the columns rows. So negative 1, 0, 1, the row negative 1, 0, 1 becomes column negative 1, 0, 1. Row 2, negative 1, 3 becomes 2, negative 1, 3, but as a column 2. And row 3 becomes column 3. So row 1, column 1, row 2 becomes column 2, and row 3 becomes column 3. That's all you have to remember. In a square matrix, it's even simpler like that, but if you had like different, it still works. You can do a transpose. Oh, A, B. So the multiplication of matrices A and B. So the coloring is really important here if you pay attention the first time. And it does not fit fully on the line, so I had to squeeze it in under it. But you get the idea still. You do basically the dot product of row 1 and column 1, row 1, column 2, and row 1, column 3, and add them together. That's all it is. It's 3 individual, or not add them together, you put them in each of the entries. So entry 1 is the dot product, is the dot product, so it's summation of 3 different things in here, so it's a summation. So it's row 1 dot column 1. Then you have entry here, the second entry in the row 1, column 2, dot product. Then row 1, column 3 for the last one. Then you repeat for row 2. Then row 3, and then you... That's all it is. It's a series of dot products. It's the best way to think of the matrix multiplication as you're doing several dot products. Yeah, so the first one, negative 1 times 0 plus 0 times 3 plus 1 times negative 1. Yeah, and that's the whole thing. Eventually that becomes negative 1 when you simplify down. And then you do it for negative 1 times 4 plus 0 times 1 plus 1 times 0. And so on. Then on the second row you get 2 times 0 plus negative 1 times 3 plus 3 times negative 1. Then you repeat again across that row. And yeah, you do this until you finish. And also multiplication, remember you have to have the same number of, you have to have A times B, you have to have A's columns and B's rows be the same. Because it's row, column, so column and row have to be the same. Column first and row. The middle of the, if you do them side by side, it goes row, column, so the middle have to be the same. The middle two. Same number of columns as you have rows. In that order. So yeah. And it also intuitively does not make sense if you try it. It honestly, if you have an eye for it, won't even feel right if you tried it. But still, this one works. It's defined and all that. B transpose times A transpose. This is an interesting one. So you can do it a little bit longer way by just doing transpose. I mean, it's not that much longer because you're literally just transposing. But you can use a property and your answer from here to figure it out real quick. So BT times AT. So we have the two things. I didn't do them in color because of how normal. So we take the transpose, of course, make the rows columns and the columns, we make the rows into columns basically. Oh, yeah. And the columns and the rows, you switch it. You do the switcheroo for both A and B, but it's B times A. So BT times AT, so you do the process here, and it's all squeezed in, but it's the same thing as before. You should get this definitely from it. Then you simplify down, and it turns out BT times B transpose times A transpose is equal to this, which is in fact equal to ABT. This is the transpose of AB here. See, negative 1, negative 4, 3, negative 1, 4, negative 4, 3. So it's the rows become a column. Such, and to keep negative 6, 7, negative 3, negative 6, 7, negative 3, 5, 1, 0, 5, 1, 0. Yeah, it's a transpose of AB. So you could just start from here and just do the transpose of AB to get this. And it would save you time, but it's not 100% necessary, but it helps, you know. On a test, you can just do that property. That's like one of the really useful properties. B transpose A transpose is equal to just the product AB transposed. So in 1315, this is a real quick one. Find each as indicated where A equals this simple matrix, 2, negative 1, 1 half, 1, 0, negative 2. So first is just A transpose. So literally 2, 1 becomes 2, 1 row. Column negative 1, 0 becomes row negative 1, 0. And column 1 half, negative 2 becomes 1 half, negative 2 row. Otherwise, you could just do it row 2, negative 1, 1 half becomes column 2, negative 1, 1 half. You can do it however you want, but you're just flipping them around. So this 2 rows, 3 column matrix becomes a 3 row, 2 column matrix. As the rule of transpose says. The columns A1 and A3 and row A2 from this, so yeah, that's just stating it. So row 1 is 2, 1. I mean column 1. Yeah, columns A1. So column 1 is 2, 1. Column 3 is 1 half, negative 2-ish. And then row A2 is just the second row, so it's 1, 0, negative 2. And that's just showing that you can label rows and columns like that. So columns are with the number above, row with a subscript. In 17 through 21, find A, B, and BA where these products are defined. So here's multiplication where some products might not be defined. So here we're given matrices A in green, B in blue here. You multiply the gamma item as carefully as possible to keep it clear. In the colors. You do your matrix multiplication like usual. You get a dot product for every entry. And it becomes just 7, negative 1, 1, 0, negative 4, negative 2, 6, negative 6, 0. And then you do B times A now. This is defined, so they're both 3 by 3 matrices, so yeah, rows, columns are the same no matter which way you multiply them. With square matrices, it'll always work. Multiplication will always work with 2 square matrices of the same dimensions. It's very intuitive. But no, so AB is given. We figured out AB. Now we figure out BA. The same method. Here, color it out. Oh, and this is another thing to remember. A times B and B times A will usually, often enough, they'll generally speaking not be the same. Now, of course, if you have identity, if you have one of these beta identities, then yeah, it'll be exactly the same. If A times B equals B times, it can equal as well. It doesn't have to be identity, but that's very rare. It's generally speaking not the case. In general, AB does not equal B times A, which is the big thing about matrices, is that it only happens occasionally, like maybe with some simple matrices, and also where one's the identity. Those are like, identity matrix is the most common case for A times B equal B times A is when one of the matrices is identity. That makes you. That's just important to state, but yeah, obviously here A, B, and BA are different. So 19, well, both are not defined. AB is not defined, BA is not defined. 2 by 3, 2 by 3. So AB, we have 3 columns, and then B we have 2 rows. 3 is not equal to 2. 3 columns not equal to 2 rows. It's not defined. BA is same thing. We have 3 columns, 2 rows. They're not equal to each other. Goodbye. You're not defined. Then 21 we have A equals 2, 1, 0, negative 1, 4, 0, and then B equals this thing. Well, this is actually the identity matrix, so identity matrix of order 3. Now, of course, as I said earlier, usually they'd be the same, but it has to be defined as well. So BA is not defined. That'll be the first one because that one's obvious. So 3 by 3, 2 by 3. So 3 columns here does not equal 2 rows. 3 does not equal 2. So B times the multiplication of B and A is not defined. So yeah, the product is not defined. But we can do AB. So A times B, you're gonna get A. That's it. Yeah, because it's a matrix times identity, and identity is applicable here. It's defined. The multiplication is defined, so AB equals A. Yeah, B equals I of order 3, which means that AB equals A times I, which equals A. Because it's applicable. Two rows. It's 2 rows, 3 columns. B has 3 rows, so it works. A times B works. B times A is not defined. But showing you the process, yeah, it does work. You have 2 times 1 plus 1 times 0 plus 0, 0. So you're going to just get 2. Same as that. 2 times 0 plus 1 times 1 plus 0, 0. So you just get 1. Again. As you can see, there's all these zeros. And when you have 0, of course. But yeah, that's how the matrices works. So, yeah. So A times B is just A, because B can be identified easily as the identity matrix. Oh, here's some fun ones now. I mean, for the next section, I kind of left out a few of the more fun ones because they get a little bit convoluted and probably not test-worthyable on a limited time budget of the test. So, find the powers of A squared and A cubed for A equals 1, negative 1, negative 1, 2. So, A squared equals A times A. This is a common saying. If you have a square matrix, all the powers are pretty much just multiplication of itself is defined. A square matrix times square matrix and on repeat. You're always going to get more and more square matrices. I mean, maybe. So you just do normal multiplication and we get A squared equal to 2, negative 3, negative 3, 5. So A cubed is equal to A squared times A. And I'm pretty sure there's a property that does not matter the order technically. You could do this in any order. I think at least. Yeah, I think you could do this in any order and it would not matter. Let's see. Just real quick, just out of curiosity. I always prefer just keeping it the higher power on the left-hand side anyway. But real quick. There's one of these matrices, so thought there was a property here, but it doesn't matter too much. Well, ABC equals the ABC. Alright, because if we split it down A cubed into A times A, like 3 separate matrices we counted, let's say. The order would not matter, I believe, because A times BC equals AB times C or something like that. Either way, we don't have to worry about this property too much. Just think about it. It works. So A cubed equals A squared times A. So eventually we get just 5, negative 8, negative 8, 13. So A squared, 2, it's just these answers. There's nothing more to say but just the answers, because it's dot product again, multiple times. why it's important you understand the basic, basic vector multiplication, because it comes up here. Oh, here's find a general formula for a to the n power when a equals 1, 1, 0, 1. So, 2 by 2 matrix. So it won't be that hard to multiply. You're basically able to rough shot this a few powers and get it. So a squared equals a times a. We do a dot product again and everything. We get 1, 2, 0, 1. So yeah, only thing that changed was the upper right, the first row, second column entry. Went from 1 to 2. A cubed. We solve, we get 1, 3, 0, 1. So again, only the upper right changed. And and then just for goodness, let's say a4. Same thing, you get 1, 4, 0, 1. So dot dot dot. We can reasonably assume a to the n power equals 1, n, 0, 1. We can reasonably assume this at this point. This is the formula for all powers of a. And this especially is true because if we were to think backwards, a to the 0, you just put a 0 there and you'd have an identity matrix, which is technically the truth. Like a to the 0 power in general is, because these square matrices is just an identity matrix. Either way, a general formula works very well for this simple example. Use your mathematical induction skills, or whatever you want to call it, to be able to deduce that this is a to the n power equals just 1, n, 0, 1. Because you have a to the 1 power technically here equals 1, 1, 0, 1s, and a2, a squared equals the second power equals 1, 2, 0, 1s, and a to the third power equals 1, 3, 0, 1. A to the fourth power equals 1, 4, 0, 1. Only one thing is changing there. It's increasing by 1 increment each time, and it's the same as the n. The nth power, whatever power it's raised to, is the same as this entry. Finally, a matrix A is called an involution if a squared equals 1. Give an example of a 2 by 2 matrix now equal to I. That is an involution. This is like an interesting puzzle type game sort of thing, like a puzzle. So you basically say the generic matrix A, like 2 by 2, is just A, B, C, D. That means a squared equals a times a, which is this same times itself. You can write it out, eventually get a squared plus bc, ab plus bd, ac plus cd, bc plus d squared. So this has to equal the identity matrix, the 2 by 2 identity matrix. Identity matrix of order 2, as it's called, a 2 by 2 matrix. So that's what an involution is, a squared equals identity. So that means this whole thing here equals 1, 0, 0, 1. So we can write that as a system of equations. A squared plus bc equals 1. This equals 0, 0. So I overcomplicated a little, but hey, whatever. So b times a plus d equals 0, or c times a plus d equals 0. Because we know this property, when you have something equal to 0, you can split it up like this. Like when you have it in this format. B times a plus d equals 0, you can form. It means that b equals 0. Or a plus d equals 0. C equals 0, or a plus d equals 0. Now, considering everything, you can try that, but it wouldn't work. If you do that, if you do b and c equal to 0, then we're going to end up with the identity matrix, basically. So let's try to do a plus d equal to 0. So a plus d equals 0 implies that a equals the negative d. So the opposite sign. So a and d are just opposite sign, but they have the same absolute value. Basically, they have the same absolute value, is one way to say it. So we can let a equals 2 and d equals negative 2. That way, it won't be the identity matrix. Now, maybe in an extreme case it'd be something different, but hey, not the identity matrix. That's what matters. We can't have, basically, as long as this is not an I, then it's an involution. Because obviously I times I would give you I. So a squared plus bc equals 1, bc plus d squared equals 1 is what's left. You can solve either one of these. what you'll get is 4 plus BC equals 1 or 4 plus BC equals 1. And I kind of made this funny, but it's BC equals negative 3 basically. It's all we have. Go with. Just both equations simplify down to that. There's nothing more complicated. There's nothing to solve really. So you can let C equal 1 and B equal negative 3 and you'll get a matrix that will work like this. So you have 2, negative 3, negative 1. 2, negative 3, 1, like positive 1. That's why I put a plus there because I accidentally, and negative 2. That matrix should satisfy it and you can double check it. This matrix satisfies the condition needed, the equal identity matrix, when you multiply it by itself. And that's it for this simple section on matrices.